Okay, hello. So this week we'll be talking about, as the title of the slideshow suggests, merging. Now, what merging is just combining two tables into one, and it's actually a little more complicated than it first seems. And just know this is also very important, as intuitively in the real world, right? All your data is not going to come in one table, right? You're going to have data from source X, data from source Y, and you're going to have to combine them to make use of compare both the data sets, right? So that's why merging is so fundamental to data science, almost as fundamental as group by. Okay, yeah. So first, since we took a little detour the past 2 weeks and we talked about like graphing and like different types of graphs, where the code was like very simple most of the time, right? I'm gonna give a quick recap from the start of pandas, because this is where we're sort of shifting back into the data frames, the tables, right? The columns. So when it comes to extraction, the square brackets are the most important, right? And the key thing to remember about these square brackets is that they're context dependent, which means that it can take in three different type of things, all which outputs three different types of values, right? So you can input a slice, which will output rows. You can input a list of columns, which will output a table, and you can put in a single column value, which will get out a series or a column, right? We also talked about filtering. One of the key ideas of filtering was this thing called a Boolean array, right? Where if you use this square bracket or dot lock, I guess, if you use the square bracket, you can put in a Boolean array to filter out things in the data frame, right? So if you see here, if it's true, if the index is true, that means you keep it. If it's false, that means you throw it away, right? So in this example of the state table right here, you see that index 0, index 2, index 4 are true, right? Which means that you see here 0, 2, 4, they're in this data frame, right? While the odds, where it's like 1, 3, 5, did not make it in this data frame because you filtered it out with this Boolean array. And what makes Boolean arrays so powerful is that you can use like a less than sign to compare a value a with a entire series, right? So you can just sort of create a Boolean array from a column, right? To do like very effective filtering. One of and the other key thing we talked about, the keyest topic, if that's even a word, the most important topic was group by, right? And the core idea, and I know I've shown you guys this like many times, and I've shown you this many times because it's very important, right? And the idea is you group by a column, right? And all the values in the column with the same value, right, would be grouped together, and then you aggregate it with an aggregate function. So in this case, we group by this letter column here, right? So then all the A's get grouped together. Then we have this like mini sub data frame, and we use an aggregate function or a collect function that sort of condenses the values into one, right? So in this case, we use the min value. So if we look at this set of A's and this column right here, what's the min of 3, 1, and 2, right? So it's 1, which is why we output 1, right? So in this case, what is the min of 12, 2, and 8? Well, that's just 2, so we output 2. If we check some random one, right? So if we check the C subdata frame, which is created by the group by, and we check this column right here, what's the min of these three values? It's 4. So the output is 4. Yeah, so like the formal definition, which I've already talked about, right? Splits the data frame into categories, applying a function to those categories, and combines the results back into a data frame. And the group by itself creates a data frame group by object, which are mini sub data frames. However, you cannot use mini sub data frames like yourselves. You're gonna have to, you sort of have to like access it by proxy using the dot aggregate function, which just aggregate just means a function that smushes a bunch of values into one, right? So that'd be like mean, standard deviation, sum. The most common ones are like first, right? Give me the first element, min, max, etc. Right? There's tons of different aggregate functions, and that's how you like sort of get this final data frame here. So that's like the quick review about what we've learned so far in pandas. And before we talk about merging tables, another core idea is grouping by multiple columns, right? And okay, I completely lied. I'm gonna first formally define read CSV, mainly because I was asked to, and for our purposes, to read in a CSV, simply just call pd.readcsv and then the name of the .csv file, right? Just make sure that your CSV file is in your alviso.edu folder, right? So otherwise, you'd have to, you can like right click the file and say copy path. It's like a copy path function. I think I put it in like one of the previous slides, copy path, and you can just copy the path, which is another string, into this read CSV file, and you can output the table like that. For our purposes, try to find a file that ends with a .csv. .json also works, but there might be like a little extra code you have to do, but Pandas is very smart and it'll sort of read it for you and output this. If you need some data to work with, I think it was compiled here, right? On this like document here that I think I sent out a little while ago. This one is like a very good example where it just has air data, right? So if we look at this pm10.csv, which I got from this website, I literally just called this only, right? And it gave me this table with the date, a crazy date. You probably want to change this to a time series, right? And then like a bunch of things about the PM10. Okay, anyway, so back to the actual topic, the group by multiple columns, which is what I'm talking about. So this is exactly what it sounds like. Instead of grouping by one column, we can group by multiple columns, right? So if we recall our baby names data set, which just has the sex of the baby, the year, the name of the baby, and then the amount of like babies that were born with that name, right? So let's suppose we want to build a table showing the total number of babies born of each sex in each year, right? Notice how this would require both the year and sex column, right? Because we have to differentiate between male and female, right, to get this, while also grouping by year, which is what we did before, right? So how do we do this? Luckily, Pandas is very convenient. We literally just, instead of putting one string in here, one column name in the group by, we literally just put a list of column names, right? So we only want to count because summing strings leads to disaster, right? We might talk about like the effects of this later on, but just know we only want the count, right? Because, well, at least the question only asks for the count, right? So very simple syntax. We just simply just add this extra column, and what this will output is, as what's intuitively correct, is that you have, instead of grouping by just one value, right? We group by pairs, right? So every time 1910 and F are together, those would be our new sub data frames, right? And every time 1910 and male are together, that would be our new sub data frames, right? So what this would output is 1910 female. Okay, what's the count of that? 5,950, which means 5,950 females were born in 1910 and 3,000 males were born in 1910. I don't know why there were so many more females than males in these years. I'm not sure why, but if you look at like 2020 maybe, or 2021, like the numbers are a lot closer, probably a lot more reliable than records in the 1910, right? So to visualize this, it's basically the exact same thing as a normal group by, right? So we're grouped by this row or this R. I don't know why they called the column R, but this column R and this column C, we group by these two, both of these. And what will happen is we'll group by pairs, right? So you see these AFs are grouped together. This AM, there's no other AM, so this is by itself, right? BF, there's only one BF, so that's by itself. The BMs are grouped together, right? And then again, we have our aggregate function, and it will condense these two values into one. In this case, it's sum, right? In our case, it's also sum. And it will sort of output the value here. And this right here is just our final data frame, right? Where you have the AF, AM, BF, BM, CF, right? In this case, we have 1910F, 1910M, 1911F, 1911M, right? So everything works intuitively as expected when you group by two columns. A little bit extra is what's called the pivot table. What the pivot table is it's just another way to visualize a table that is grouped by exactly two elements or two columns, right? And the syntax of this is you call it dot pivot table. You specify an index, which is just a row, right? You see here. You specify the columns, which is just the columns of your new table, right? The values, which is the values in here, right? And an aggregate function, right? So if you notice, it's very similar to you have an aggregate function. Your values are here, and your two group bys are here, right? Now, the reason why pivot tables exist is that they're like a lot more visually pleasing to look at, right? So if we look at this, we have the year on our y-axis, and we have the sex on the on the x-axis, right? So, and if we look here, 1910 and female, right? The count is 5,950, 1910 male, the count is 3,213. If we look back at previous example, those were these exact numbers right over here. So yeah, so it's basically representing the exact same information. It just looks like visually pleasing, right? So a pivot table visualization, this 75% of the table is exactly the same as what we just looked at, right? The only difference is that how the values are placed in the table, right? So this 5 goes here, right? So this A, B, C, D go here, F and M go here, right? If you see this 1, instead of going like in a table stack, right, it just goes in this nice table. Notice that if there's no pairs, it'll have a NaN value, right? Instead of just not in this case, there was just no row, right? But in this case, there's a NaN value. Pivot tables also have access. You can also sort of have multiple values, right? So instead of just the count, let's say I wanted the name and I wanted the max. So with the max of the name, just that will imply is that it's like the largest lexicographically, meaning that it's like closest to the end of the alphabet, right? Like string wise. And the max of the count is the largest count, right? So in this pivot table, we have 1910, right? And female, we have 295, right? And then in this case, we can also have the 1910 and then female, and then by name, the largest lexicographically name closest to the end of the alphabet is this name Yvonne, right? But keep in mind that we took these two values separately, right? So this 295, which is the max count of a name in a female name in 1910, has nothing to do with Yvonne, right? So we've computed these values completely differently. However, this just shows you that it's completely possible to just have sort of a longer pivot table, right? Where you have multiple values instead of just one value here. Yeah, okay, so this is like a little bit what I mentioned before. So like, why does the pivot table even exist, right? it's the same information as the group by two values, except it just looks better than this, I guess, right? So like this clearly looks a lot better than this. Also, but keep in mind that when you group by, you can group by more than two columns, right? The pivot table is limited to only two columns. You only have two axes. You can't make a 3D pivot table, sadly, right? But a group by, you can group by like 27 columns if you want, right? Just to group by those like 20. It might not be that interesting, but just know it's very possible, right? And in the real world, you're gonna have to group by like 4 or 5 columns, right? So that's why group by is normally a lot more used than the pivot table. All right, so now finally to the big topic of today, which is merging/joining tables. So merging in general. So why is merging even important? I touched on this a little bit at the beginning of this lecture, right? So in the real world, you almost never get all your data in one data set, right? But what if you want to make comparisons with data in different tables or different data frames, right? You have to merge the two tables together. Now in pandas, also this like the merging idea as joining idea comes from this language called SQL. In pandas, however, there are 5 types of merging. It's called the left merge, the right merge, the outer merge, the inner merge, and the cross merge. I think most people use join, right? So they call it a left join, a right join, an outer join, an inner join, and a cross join, right? And each 5 of these different merges has their own unique cases, right? So the syntax for merging is this very convenient function. It's called pd.merge. And there's 2 different syntaxes that you can use. You can either put a data frame here, which is the quote unquote left data frame, and called .merge on it. Right? You specify the right data frame, and then you specify which 2 columns from the 2 data frames you want to merge on, which just means if you have like sort of like an ID column for both of them that like specifies which ones you want to like, which rows you want to combine with which rows, right? This is how you do that, right? And this how parameter just chooses which type of merge you want. So the other syntax is just called pd.merge, and you specify the left data frame inside the function call. In practice, you can do whatever you want. I've seen both of these used quite often. And there's really no advantage to these 2 at the very least. Right. So let's talk about what the types of merges are. The first one is called inner join. Now, this is the default behavior. So in the previous function, if you do not specify this how, right, it will just simply assume you want an inner join. Now, what the inner join does is that if left call val equals the right column value, create a new row with all columns from both tables, right? If there are no matches, simply do not add it to the new data frame. Now, this is very important, right? This means there's potential to lose data, right? Because there's no match. Right, so in this case, our S, this dummy table, we have this S and T, right? And we merge on ID, right? So when I say left on, I mean this ID column right here. So I'd put ID here. Oh, sorry. I'd put the ID here. And when I say right on, I'd put ID again, right? Because this is the ID of the right table. Right. So, and these, when I look for matches, this double equals. What I mean is that it'll try to match this ID column with this ID column, this T's ID column. Right. So in this case, we look for 0. There is no 0, right? There's no 0 in this ID column. Because it's an inner join, we would throw it away. So notice in the final table, there is no 0, right, anywhere in this s.id. If we look at 1, right, we try to match it right here. We see the 1, right? Right, so then we'd output this, right? So we have the s.id, which has 1. we have the boots, which is from this S table. Then we have this TID, which is from the T table. Then the breed, which is this also from the T table, right? And you'll get these two redundant columns, so you normally have to drop one. A very important thing is that when you call your left on column, your columns are unique, right? It's sort of like the defining column of the table. Because there'll be like a lot more unpredicted behavior if you have, for example, two values of 1 in this table, right? I forgot the exact behavior, but you literally never call join on, and you never use like a column that has duplicate values in it, right? So if we look at 2, you see that 2 matches with this column right here, or this row right here, right? So you get 2 Kali, 2 Ragdoll, right? So if we look at this table, you get 2 Kali, 2 Ragdoll, right? As intended. And lastly, if we look at this 4, it's 4 Eugene and 4 Bengal, right? These two are matched, and you see them here. Notice that in the T table, there's this extra ID, this 5 ID, right? This ID, since it had no match in the S table, is simply thrown away. And again, this is very important because you're losing information, right? So if you merge these two tables with an inner join and you use this final table, then this ID 0 apricot and this ID 5 Persian are lost, right? You will not be able to find it. So if you ever like try to look for it later, you realize you've lost data when you've merged these two tables with this inner join. Now, another type of join is what's called a cross join. Now, the name comes from the cross product of vectors. I don't know if you guys learned multivariable calculus yet, but the idea is that I simply do not care what the value of my column is. I simply just pair it with literally every single other row in the other data frame, right? So I merge together every possible combination of rows. So now what this would look like is that this ID, this 0th row, right? I would simply pair with literally every single row in this T data frame, right? If we look at here, zeros, right? There's 4 instances of this, and we have the entire T table right here. Same thing with 1, right? I simply say, okay, 1, I pair with literally every single row in this data frame. If we look here, right? And at first glance, this might seem completely useless. Like, why did you just like double the size of like your data, right? For like fun, I guess. And to be honest, I've never had to use a cross join in practice. But there's this very nice Stack Overflow thread if you guys are curious on like the different instances of cross join. One example I can think of is if you want to create a grid and you want to like populate a grid, right? So you want to assign a color to every box in a grid, right? A cross join would be very effective at that, right? Because you're considering like every possible pair, right? We need to consider every possible pair. That's an example where you have to consider every possible pair, right? But yeah, another key idea of the cross join is you don't lose any information, right? Notice that all 4 of these rows in S and all 4 of these rows in T are in here. Now, importantly, if you filter this final table and say like SID equals TID, right? And you only want to keep those rows, what would result is an inner join, right? So if I say I only want to keep the rows where SID is equal to TID, right? So then this part gets deleted. Only this one, and this one would get kept, right? The rows would get kept, and you'd end up with what we saw earlier in the inner join. Right here. We end up with this table. Now, another type of join is called the left join. Now, this one is a little more complicated. Now, instead of just doing this madness of combining everything possible, I state that if my values are equal, I will create a new row with all columns from both tables, like the inner join, right? If there's no match from the left table, I still create a new row with all columns, but with the right table's columns as null, which means I didn't find it. If there's no match for the right table, I simply do not add it to the data frame. Now, at first glance, this seems kind of weird, right? So like, well, I guess like, what? Yeah, like half our table is going to be empty if we don't find a match, right? So I guess what this means is that it's very similar to the inner join where I have these three rows. I find the match in the other table right here, and I find the match in the other table and I simply put them in. Like, so this is the behavior as a normal join. However, what's new of the left join is that in the left table, if I do not find a match, I would still add it to the table, except I would add these null values here. So in this case, this ID 0, right, apricot, there is no other ID with 0, which means that I will put you in the data frame, but assign these values as null. Now notice on the right data frame, this 5 also does not have a pair. However, because it's a left join, this 5 does not get added into the data frame, right? So what this means is that what you assign as your left table and what you assign as your right table matters, right? In the cross join, it also matters as well, right? If you notice this ordering, it's ordered perfectly by the S table, right? But that's like up to like an ordering, but it's like still the same table up to a permutation, right? In this case, it's a completely different table depending on what you specify as your left table and what you specify as your right table. So intuitively, why a left outer join might be useful is that, let's say your left table is players, right, in a video game, right? So like all the players, you have like a player ID, you have like their stat or whatever. And your right table is, for example, a player's purchase history, right? So they'd have the player ID, and then they'd have like how much they spent, etc. Right? However, not every player has an entry in the purchase history, right? Because not every some players are free to play, right? However, you don't want to just simply delete the player, right? So you leave it here, and these null values will simply signify that they have not paid, they're free to play in the game. All right, so this is like an example of a very nice example of like a left join. Now, there's also a right join, which is literally the exact same thing as the left, but instead you switch direction, right? So instead of if there's no match for a left table, now if there's no match for a right table, create a new row with all columns, but with the left table's columns as null, right? And if there's no match for the left table, simply do not add it. All right, so what this would look like is very similar to what we just saw with the left outer join, right? Where in this S, right? So this apricot or the 0 ID does not have a match. So, but since it's a right join, it is thrown away. In the previous example, you see it made it into the table with these no value. Right? But in the right outer join, it's thrown away. And these three with matches will still match, right? Like an inner join and get output in our final table. And finally, this ID of 5, which is does not have a match in the left table, but is in the right table, will get added into the final table with these two null values, right? Yeah, so this is like sort of like an intuitive example I literally just mentioned. That one data frame of users. The second one is purchase history. Not all users have purchased something. but you don't simply want to delete them. The reason why I gave this example, by the way, is because this was like a project I actually did in high school where I looked at like League of Legends accounts and I was comparing like or sorry, not League of Legends. It was like a Chinese MMORPG called like Dragon's Nest or something, and we were checking or we were trying to see if there was a trend in like win percentage, like skill and purchase history, right? So like this is an example where you use a left or a right join. Finally, we have the outer join. This is just the left join and the right join combined into one. Right? So if left call val equals right call val, create a new row with all columns from both tables. Right. So this is from the inner table, the inner join, right, or the inner merge, right? So if there's no match for the left or right table, create a new row with all columns, but with the right, let's just say right table or left table column as null, right? So in this case, we have this both these two same tables, right? Where now 0 still does not have a match. However, it's get added, and this 5 here also doesn't have a match, right? But it still gets added with like null values, right? So one important thing to note is that the left and right outer joins lose information still, right? So in the left join, in this left join, you lost this row here, right? This 5-person row. In the right join case, you lost the 0 apricot row. However, in the outer join, you don't lose any information at all, right? So your 0 apricot still remains here, and your 5-person still remains here, right? So this is why outer join is like definitely like the second most popular type of join, I would say, right? So the most important one is definitely inner join. There's a reason why Pandas defaults to this, mainly because people are sort of okay with losing like these rows a lot of the time, and mainly because when you try to join tables, you try to have like a perfect bijection. Okay, that's a big word, but perfect like mapping to each other, right? So like one column to one column, right? So you don't lose any information by this like inner join. But yeah, the second most popular is definitely the outer join because you don't lose any information, right? So if there was like a purchase history where that player was not in our user database, that'd be kind of concerning, right? Because actually that wouldn't make any sense. Because how can it like not a player make a purchase, right? But if that were to exist, we would find that sort of as a bug, right? So in our data, which actually happens a lot more than like a lot of data is like very not clean, I guess. But anyway, right? So in this case, the outer join, just to reiterate what I just said, the 0 gets added, but with null values, and the 5 also gets added with null values, right? So you don't lose any information. Now, these are what we just went over was all types of joins, and there's this very nice graphic that all data scientists like to use when they start learning joins, right? Where the inner join is just when both of them match. So if you guys remember the Venn diagrams from elementary school, right? So when they both match is here. In the left outer join is when it's all the left data entries and the data entries where the right matches. Right, the right one is just the left one the opposite. Right, all the right entries, all the entries in the table on the right, with the entries where it matches with the left. Right, and the full outer join is just have entries in all tables, but combining the entries that match. And what's missing here is the cross join, which just to reiterate is like joining or just getting every possible pair of the two columns, right? And a quick review on the syntax, right? So you've merged, you specify your left table, you specify your right table, so which column you want to merge on. In our examples, we always chose this ID and this ID column. And then to specify what type of merge you want, you just specify like this how equals, right? And so basically all these different types of merges we just looked at, we literally just change this one keyword and we get that other type of merge, right? Yeah, so this is like just remember this graphic. This is like the sort of important graphic on like what the merges do. And like I said, the most important ones are definitely the inner join and the full outer join. Yeah, so that's all about joining. And I have this little extra snippet today about custom sort because I sort of not forgot to talk about it when I talked about pandas earlier, but it's like sort of a harder concept, but it's very important, which is why I like wanted to take some time today to at least to mention it. Right. So okay, so first of all, like why custom sorting, right? Intuitively, it's pretty obvious, right? So like what if I want the longest names and baby names instead of, something I can sort by like numerically, right? Or I want like the largest of some custom sort metrics, right? For your guys' case, if you look at the Alviso data, a lot of data is California's entire data, right? So how do I get the data points that are closest to Alviso? Okay, that's a typo there, but ignore that. How do I get the closest ones to Alviso, or close to Alviso, right? So I would have to sort of sort it by distance, right? From like, because you're given, well, the data type I looked at, it gave you like position in longitude and latitude coordinates, right? So you'd have to like sort of calculate the distance between them, and then you have to sort by that like custom distance you just created. So approach one, and probably the most intuitive approach, if you're, I guess, like a beginner when it comes to Python, I would definitely recommend this approach. It's definitely, like I said, the most straightforward approach and the most intuitive approach, where I simply just create a new column and I sort by that column, right? So let's say I want to sort by the longest name in baby names, right? So I want the longest names first, I want the shortest names last, right? So what I do is I just create baby names name length, right? This new column name, and then I would just call dot string dot length, this dot stir length, right? Just know that this returns a series of the length of the string in name. Next week we'll be looking at, well, actually, plans have changed a little bit, but next week we'll be looking at assignment, and if we have more time, we'll talk about like all these different string functions we can use. And this turns out to be quite important as well. But for now, just know that in that index, right, it'll return like the length of that string of that index, right? And it'll list it out as a series, right? And now I simply just sort baby names by that new column, right? And if I don't want this later on, I can just simply drop it after I'm done with it, right? So if we look at the final result here, we have the longest names first because ascending equals false, right? So the longest name ever created in California is Francisco Javier, okay? Or I don't know whose name. Actually, there's like multiple years of Francisco Javier, okay? But these are actually all tied because they're all length 15. So you can like tie break in a different way if you want, but I think this is tie breaking by year. Okay, actually, I have no idea what it's tie breaking by. It's just tie breaks this way for some reason. Oh, by count, maybe? Yeah, maybe by count. So Francis Javier and Ryan Christopher. And as you see at the end of the table is our shortest names, right? So Ha, Ha, and Lu, AJ. I don't know who named their kid Ha, but apparently 5 people did in 1990. So intuitively, right, this makes perfect sense. You just simply add a new column and you simply sort by that column. So hence a custom sort, right? But of course, this is the hardest part. How do you get like the new column, or how do you like create the new column? And this will be like taught more in approach 3, I guess. So approach 2 is the sort value has this what's called a key parameter, in which case you can sort by a function, right? Or like by a column and then sort by that column by a function. Now, this requires a lot more Python knowledge. So if you don't know that much Python, it's okay. You can just go back to like the previous approach. So what this approach is in the key parameter, you can put in a function that sort of gives you a value to that specific value in that column, right? So in this case, if you guys don't know what a lambda function is, just think of it as like okay, actually, yeah, right here. So this lambda x, x.string.x length, if you're not familiar with Python, just know that this is literally this function. Define length of x as return x.string.length. Okay, so what this does is that it will call this function on every single value in name and order it by the output of that function, right? So in name, you have Francisco Javier, right? So it would go into this function, you call this function, it would output 15, right? And save that 15. Then it will call on like Jesse, right? It put in Jesse, Jesse will go in here, it will output the length of Jesse, which is 5, right? And then that's like the quote unquote value of Jesse. And that's like the quote unquote value of Francisco Javier. So at the end of the day, when all these values are created, this will simply sort by that generated value. Now, as you can imagine, this gives you lots of power, right? Because this allows you to sort of sort by whatever function you want, as opposed to just like string.length, for example, which is what like the previous example said, right? You can do like lots of funky things just by like, hence the name custom sorting, right? The third approach is the map function, which is sort of similar to the lambda function, except it's like sort of more concrete and even more viable, I guess, right? So there's this function called series.map, which again, if you're proficient in Python, you already know what the map function does. But if you're not, that's okay. Keep in mind, this is completely different from the Java's map, but it's very confusing. I get confused with it all the time. But the Python map, what it does, it applies the function to every element of the series. Right? So exactly what the Python.map does. Right. So this sort of allows us to use approach 1 more effectively, or like more obviously. And this is just like this one, but more concrete and like more cut out. Right. So to like give you an example, right? So for example, if I want to find the name with the most amount of A's in it, like the letter A, right? Okay, that's another typo. I can use the map function to create a new column with the counts of A, right? So I create this new column called A count, and I call this .map function count A. So what will happen is every entry in the name column will go into here. I'll count the number of A's, and that'll be its new value. Right. So if we look at this, like this name here, Maralejandra, right? How many A's are there? There's 1, 2, 3, 4, 5, and I'll output this 5. Turns out this is actually surprisingly low. Okay, so it turns out the name with the most A's is this 100, and it's 5. Right, so now I can do something similar to approach 1, which I simply just sort by the values of the new column I created, and put ascending equals false. Right. So this is like sort of like some insight on custom sorting. Like I said, it's sort of important and it's also like very niche, right? So like in this case of like, for example, this Alviso case, right? So how I use this is that you'd have your longitude latitude, you take them in as pairs, or like maybe you can combine them into one column if you want. You'd input that into here, and you'd in here in this function, you'd calculate the distance of those launched latitude coordinates from Albedo, right? And you output that distance. And the distance can be whatever unit you want. It just has to be consistent, right? And now you can simply sort by that distance that you just created with this function, right? So that's like sort of like a little insight on why you need to custom sort. And I believe that is all for this week, right? Okay, yeah. So next week, everything to do with strings. This plans might have changed. The current plan is I'll create an assignment because you guys definitely need practice with what I'm teaching you. So that's like what we're going for next week. And well, the plan is I'll start the assignment next week and you guys will finish it after. And if you guys are too busy, because I know it's like A/B testing season, that's okay. You can take your time, I guess. So I guess I'll quickly recap what we went over today. We went over grouping by multiple columns, right? Grouping by multiple columns, which is this graphic here. This is like the key graphic. We learned about pivot tables. We learned about the 5 types of joining, where, like I said, this diagram is conceptually what's going on, where the inner join keeps both everything. The left join keeps everything in the left table, and the ones that are equal to the right table. And for outer join doesn't lose any data at all. And then you have the cross join, which has every possible pair of the 2 columns, right? And we learned a little about custom sorting. These definitely require a lot more Python knowledge about like functions and stuff. But if you're familiar with Python, this will be like a great tool for you. And yeah, that's it. Right. Thank you. And I will see you guys next week with a new assignment.